All right, let's do.
Okay, so let's talk about some preliminary. Yeah, I'm going to be raising my hand. Oh, you know what I'm talking about. I'm going to be doing this a lot today. Because we don't have the linear algebra or the real analysis to actually talk about anything in complete detail, but I do want to give you guys some ideas of how things are fitting together. And kind of start with what some objects are. And again, I'm still not going to be very specific about it. If you take a class like 346, you'll actually get the specifics of a lot of what I'll talk about. So there is something called a vector space. It's basically a set. Oh, before that, let's talk about a field. That's like real analysis. Maybe they talk about it a little bit in 346, but it's basically right. Handwavy a set with multiplication. The multiplication can be defined differently from what you're used to, but there's something that's analogous to multiplication and addition that behaves like the real numbers in terms of what the properties are. So the real numbers is an example of a field. Other examples of a field, the complex numbers are examples of a field. The set of integers is not an example of a field. Why? It doesn't behave like a real number. Well, what do you mean? If I take one integer and I divide by another integer, I don't always get an integer, right? If I look at a list of integers, I take the integer 2 and divide it by the integer 3, I get something that is not an integer anymore. This never happens with a real number. If I divide a real number by another non-zero real number, I always get a real number, right? So that's kind of what I'm talking about. You add two things, you get a member of the set. You multiply something by a scalar, you get a member of the set. You have division by all non-zero elements being a thing. Division is actually quite rare. It's very special when we can do that. And so the real numbers have all the nice things about real numbers that we love is because they are this thing called a field. And there's a list of properties that make something a field, and it's pretty much the list of properties of the real numbers that we all like. The members of a field are called scalars. So that's what a scalar is. When someone says a scalar or a constant, they are just referring to the member of a field. Now, for pretty much all of your mathematical life, scalar does make a real number to you. That's because all your mathematical life, the field you've been working with, is the real numbers. When you go to abstract algebra, that's not going to be true anymore, and field and constant and scalar, they'll take on a whole new meaning. Now, there is the idea of, so this is one idea that we want. A set that has two operations like multiplication and addition that behave like the real numbers, we call them a field. The elements of this field, we call them scalars or constants. The next thing you want to talk about is something called a vector space. Now, this is a set with a field, and it has things like addition and another operation called scalar multiplication, which means you take a member of a field, you can multiply a member in the set, and you get another object in the set. It does not have any definition for multiplication. You just know how to add two things and how to take scalar multiples. So this is a set with a field, and that behaves like Rn. So you think of vectors from Calc 3, three-dimensional vectors and all that stuff. All the things you could do with vectors, Those are all some, anything that behaves like that, we call it a vector space. And the elements of the vector space are, we call them vectors. Now, not vectors in the sense that you're probably used to, but they would have the same properties as vectors that you're used to. Some non-silly examples here. Set of n by n matrices with real entries. Form a vector space. Think about it. You add two matrices of the same size, you get a matrix of the same size, you can multiply by a scalar, you get another matrix. Division isn't a thing, which with vectors, division isn't a thing, right? I can't take a vector in R3 and divide by another vector in R3. You can't do that with matrices either, because matrices are not a field. Matrices are what we call a vector space. They form a vector space. So I can look at all certain sizes of matrices, and they would form a vector space. Polynomials with real coefficients also form a vector space. Also notice that division will not work. You divide two polynomials and generally get a rational function, so there's no such division because it's not a field. If it was a field, division would give me a polynomial all the time, but it doesn't. However, I can add two polynomials and I'll get another polynomial. I can multiply a polynomial by a scalar, I will get another polynomial, and it will behave in general like other things. In fact, you can kind of think of polynomials, say, quadratics. You can think of a quadratic like a2x squared plus a1x plus a0. You can take an element there, and you can literally just call it a vector, a2, a1, a0. And you'll notice that everything you can do with a polynomial, you could create an entire theory where you're just pushing vectors around like this, where you just know the first coefficient corresponds to the x squared, the second entry corresponds to the coefficient of x, and the third entry corresponds to the constant. I can add two things like this, I can multiply them, I can multiply a constant and solve equations with the guys like these. I can literally translate the objects I'm looking at into vectors. Very similarly, if I had a matrix over here, A, B, C, D, I can think of it as a vector, A, B, C, D, right? Where I just know that this is the top left entry, that's the top right entry, that's the bottom left entry, that's the bottom right entry. And everything you can do with matrices, you could literally go around and do it with these vectors and nothing would change, right? They're equivalent to vectors in some sense. So you can actually think of them as they're vectors.
I have a question.
Yes.
Are we going to learn about Gaussian elimination?
No. I don't know if I might mention, but no, I'm not going to. So that's also important. By the way, solutions to differential equations form a vector space. That's going to be important for us later. All right? And I can look at all functions that are infinitely differentiable to form a vector space. There are a lot of things that form vector space. Okay. So ultimately, a lot of things, if you understand what has to work with vectors, you'll understand that why differential equation is going to work out the way it does. So for example, when I have an nth order differential equation, basically what that means is the guys that I plug into that, I can make them equivalent to vectors of size n. And so now when you start talking about solutions, basically what you're happening is you have a solution in each coordinate. There's going to be n of them. Could there ever be more? Well, no. That's like you telling me there's a fifth dimensional vector living in three-dimensional space. It doesn't make sense for there to be more. Also, it doesn't make sense for there to be less. If it has 4 coordinates, I need to fill it with 4 coordinates. It has to be exactly n coordinates because it's equivalent to a vector. What we've been doing with R3, it has to work here as well, because if you go through the properties of what make a vector space, the solutions to the differential equation will fit all of those properties. So that's ultimately where we're going. So there are objects that we can think of as vectors in the sense of all of the things that worked out in Calc 3 that are not traditionally called vectors, and many things, including solutions to differential equations, will have this behavior. And that actually starts to tell you give you a lot of certain intuitions into things. What else do I want to mention at this point? Okay, so let's talk about linear combination. But V1, V2 always be a set of vectors. And I'm putting this in quotation because I don't want you to think of them as literally vectors. It could be a list of polynomials, could be a list of differential functions, could be a list of solutions to a differential equation, could be a bunch of matrices. You don't know what these guys are. They might not be traditional vectors. Then, the expression C1V1 plus C2V2 plus CNVN is called where the Ci are scalars. Remember, they're just members of the field over which the vector space operates. It's called a linear combination. So when we looked at last class, when I spoke about, oh, we have two solutions, y1 and y2, and then we showed that c1y1 plus c2y2 was also a solution, this thing was me forming a linear combination with the solutions of the differential equation. So anytime I do create an expression like this, it's called a linear combination. Does this say CI? CI, yeah. All the CIs. C1, C2, C3.
Oh, okay. Is that different than a span?
Yes, it is different from a span. I don't think I'm going to talk about span, but yeah. Spanning just means that you can get any vector in your vector space as a linear combination of these guys that we have. So for example, you can say this spans R2 because literally any vector in R2 can be written as a linear combination of those guys in this particular way. Right? So I can say this spans R2, meaning anyone in the space can be written as a linear combination of the guys I just wrote down. I can say that list of guys span the space. I don't think that's important for us though. Now, we say V1, V2, Vn are linearly independent if the only solution to this equation, you're basically going to create a zero linear combination. By the way, the existence of a zero, quote unquote, is a part of the definition of a vector space. You have to have an object so that when you add it to all other objects, it doesn't do anything. It's called the additive identity. So the only solution to this equation equals 0, and you can think of that in quotations. That 0 could be a 2x2 matrix with 0 entries. It could be the 0 polynomial. It could be a 5-dimensional 0 vector. You don't know. But the only solution to that is all the C's must be 0. If any one of these C's are non-zero and gets that thing to work, we say they're linearly dependent. So independent means that this only has one solution, namely what we call the trivial solution. This is called a trivial solution. So, and as long as that only has a trivial solution, we call it linearly dependent. Specifically, here's something I do want to point out, because we are dealing with second order. For two vectors, this means one is not a multiple of the other. And you might be able to think about why. Suppose C1 V1 plus C2 V2 equals 0, but some Ci is not 0. Say C1 is not 0. What that actually means is I would be able to solve for V1 by subtracting both sides. Adding it to 0 is not going to make a difference. And then dividing by the C1. Because it's non-zero, I can divide by it. So what I end up finding is that the V1 will be a constant multiple of V2 if I allow one of the C's to not be 0. So as long as they're all 0, I would never actually be able to do that. I would never actually be able to write one vector as a constant multiple of the other. And to know this characterization is very convenient because, as I showed you last time, if I know one thing is a solution to a differential equation, a constant times that thing is automatically a solution. It would be redundant of me to give you two solutions where one is a constant times the other, because I've really only told you one solution, essentially. So basically, when we find solutions, we want to make sure that they are linearly independent, so that none of them is going to be a constant multiple of the other, or more generally, none of them will be a linear combination of the other. Because if I could solve for one of these guys in terms of all those other guys, it means I don't need that guy. Right? He was redundant. He shouldn't have been there, because I can just create him from what I already had. Right? So we don't want any redundancies here.
Question.
Yes?
I don't know if I'm missing something, but isn't it redundant to have all the constants just equal to 0? Like, it'll just be 0 equals 0?
Yeah, but there are other ways. The point is, there are other ways to get 0 without the constant being 0. And that possibility is what you don't want.
Okay.
Right? So like if I look at two, like counter example, look at the function y1 equals 2e to the 3t and y2 equals 5e to the 3t. It turns out that I can take minus 1/5 times this guy. No, sorry, 5/2 times this guy plus 1 times that guy, and I get 0, right? So there's a way for me to find non-zero scalars so that when I multiply them and add them together, I get 0. We don't want that to happen. Because what it means is that these guys are essentially the same thing. You haven't really said anything different. They both behave like e to the 3t. That's why you got it to work. So once you tell me e to the 3t, don't tell me e to the 3t again. It's the same, right? Now the thing is, if this was different, like this was e to the 5t, that's not going to work, right? So if you tell me e to the 3t and e to the 5t, now you told me something new. Now you told me something different. Now you told me something that's not redundant, right?
I have a question.
This characterization guarantees you won't have redundancies. Yeah.
Is a zero scalar the same as a zero vector?
No.
And how is the, because all the C's are 0, right?
Yes, because the C's are scalars.
So wouldn't the, on the left side be just a zero scalar because you're multiplying the 0 by the vector with the 0 vectors?
No, they'd be vectors. Like if I take 0 times vector 1, comma 2, what's the result? It's 0, comma 0. It's not 0. Right.
I have a question.
The 0 vector might be a scalar depending on what your vectors are, right? If my vectors are polynomials, then the 0 vector is the 0 polynomial, which is just the number 0.
Question.
Yes?
Up here, are you describing linear dependence or independence on the top right? Very top.
You mean the top here?
No, on the right. Is that dependence or independence?
Independence. This is specifically for 2 people. So I just basically restated that as this. So if I can find non-zero things, this would mean a dependent.
I mean the one where you say that they're not a multiple of the other. So let's say that they are multiples of each other.
Then it's dependent.
Got it.
Yeah. Just think of a linear independent means no redundancies. Dependent means there are redundancies. Because one essentially depends on the other. I can find one in terms of the other. So that's where the language comes from. Okay.
Which one has redundancies?
Huh?
Which one is redundant?
Dependent is redundant. Okay. Now, where do you want to go with this? Okay. So y1, y2 are dependent. If you have y1 equals e to 3t and y2 equals e to 5t, these are independent and linearly independent. Anyway, we're going to figure out a nice way for us to determine this pretty quickly. This is called the Wronskian, which I've asked you on a couple of quizzes now, but I'm going to describe how that actually, eventually, how that actually gets us to talk about independence. Now, here is the thing. There is also something called, do I want to tell you that at this point? Yeah, I guess. There's something called, the third thing I want you to know about is something called Cramer's rule. Now, you probably know what this is. But it's going to be a very useful device for us to actually think of things in terms of. So, yes.
Is this the same Cramer as Seinfeld?
No, that's with a K, right? The Cramer from Seinfeld is with a K. It's not the same guy. So given a system of linear equations, so like a11 x1 plus a12 x2 plus da 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 plus a1 n xn equals b1 da da da. So we have a bunch of linear equations. n1 x1 plus n2 x2 plus da 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 plus a n xn. We can write this in a matrix form.
Doesn't even have to be the input.
No, they don't have to be. For Cramer's rule, yes. But I'm actually introducing the idea of writing in a matrix form. You can write this as something like the following. A11, A12, A1n, all the way down into AN1, AN2, ANn, times the x1, x2, all the way down to the xn, equals b1, all the way down to the bn. And this is called the matrix form of the system. Now, if n equals n, we say we have a square system, and then once you have a square matrix, a lot of things become available to you that are not available to non-square matrices. such as this thing called the determinant, which is a way to measure. If you were to imagine that each row of the matrix was a vector in an n-dimensional space, the determinant is a value that gives you the volume of the parallelepiped spanned by those vectors, which is actually coincidentally quite useful in solving systems of equations. Now, if n equals n, we have a square system and we can find determinants. Now, given a system AX equals B, now this is just a general characterization here. I'm pretty much calling this guy big A. I'm calling this guy the vector X. And I'm calling this guy the vector B. This is called a coefficient matrix because it has all the coefficients. That's called a solution matrix because that would be the solution, that the thing you want to solve for. This is called a constant matrix. We have the following. Okay, so now I'm going to state Cramer's rule. This is all going to come together eventually. If not fully by the end of this class, by the end of next class. Because now I was talking about vector space and all this stuff, and you probably wonder why did you even tell me about that, but it's all going to tie together. We have the following. We have Cramer's rule. Set D equals the determinant of A. I assume everyone knows the 2 by 2 determinant. The 3 by 3 determinant is kind of like what you did with a cross product, and you can go bigger, which I don't think I'll ever ask you to do, but it's just a way to compute a number associated with the matrix. Set D equals to the determinant of A. Set dxi to equal the determinant of AXI, where AXI is the matrix A with the ith column replaced by B. Then the following holds. If D equals 0 and any di dxi not equals 0, the system is inconsistent. The system will have no solution in this scenario. 2, if D equals 0 and all dxi are also 0, the system is dependent. Dependent means you will be able to find infinitely many solutions. This basically means you have 2 lines in there and one was a multiple of the other. So pretty much every coordinate on one line is also a solution on the other line. You have an infinite number of solutions. Now there is a third scenario. If your D is not 0, the system has a unique solution. Meaning there is one vector, there's one set of coordinates that solve that system. And in fact, this is something that we're going to use later. We know exactly what the solution would look like in this situation. the system has a unique solution and it's given by the variable xi, so it could be the x1, the x2, or whatever, is going to be given by d of xi divided by d. This will be a unique solution. There will only be one. That actually covers all three scenarios for any linear system of equations. If I give you a random system of equations, only three things will happen. Either it has no solution, like if you have two parallel lines that never intersect, or you have infinitely many solutions where you have two of the same lines all overlapping, and of course you can go in higher dimensions here. Or you have a unique solution, meaning the lines are non-parallel and they cross at some point, and there's going to be one coordinate where they touch. That is called the solution. It's going to be the unique solution. And regardless of what dimension you're working in, if you are in a square system, this will be what the solution is for each variable.
So the
Yes.
solution will be a scalar number? It's not.
No, it's going to be a vector.
Okay,
So remember, the solution, remember, is a vector.
right.
It's a vector with x1, x2, x3, all the way down to xn. Right? So I'm saying for this one,
Oh, okay, okay.
replace the coefficient matrix with the b, find the determinant of that, and then divide by the d. And that will give me the number here. Then do it for here, and then for here, and I can fill out everyone there, and they'll all be given by that equation. Okay, so that's, is it important for me to give an example? I don't know. Let's do an example. X plus y equals 3, x minus y equals minus 1. Here's what you would have. Your a would be 1, 1, 1 minus 1. Your x would be xy. Your b would be 3 minus 1. What we can do is we can compute the d. This is just the determinant of this guy. For 2 by 2s, you cross multiply. So it's minus 1, that's minus 2, which is not 0. So what that means now, what I'm going to do is I'm going to find b sub x. What that means is I'm going to take the b, I'm going to replace the x column, all the guys that were the coefficients of x. And I would have 3 minus 1, 1 minus 1. Find the determinant of that, minus 3 plus 1. If I were to find a dy, it means I take this, replace the second column. That is going to be minus 1, minus 3, that's minus 4. And so this would mean x is actually equal to minus 2 divided by minus 2, which is 1. And your y is equal to minus 4 divided by minus 2, which is 2. And you can check. 1 plus 2 is 3. 1 minus 2 is minus 1. That gave us the unique solution. If I were to sketch these two lines, of course they would look like this. And they will cross at the coordinate 1, 2. So that's Cramer's work. And this can work in any size, once it's squared. If you have 2 equations and 2 unknowns versus 3 equations, 3 unknowns versus 17 equations, 17 unknowns, this idea will work and it will get you to the specific coordinate that solves your system. You would be able to say the coordinate xy equals 1, 2 is the solution. And you know what? It's the only one.
Can you force a square by using zeros?
What?
Can you force a square
No.
by using zeros?
And using zeros are bad because that will create a zero determinant. So, no. Yes?
Can we do an example with 3,
No, not right. Right now, probably never. I'm not sure. I mean, I've already taken up a lot of time talking about stuff that I'm probably never going to actually ask you to reproduce, so I don't want to waste even more time. If there ever comes a point where you have to do this for 3 things, I'll actually just point you to one of my videos where I teach students 3 things and you come to class and do it. It's not hard. I thought I saw that. I just not. Okay, let's see. What else can we say now? So that has a unique solution. Now, let's talk about systems of first order ODEs. So let's say I have a bunch of first order ODEs. And of course it's going to be linear here. Okay, so let's say I have, here's a function y1 prime. It is a constant times the function y1 plus a constant times the function y2. And say I have y2 prime, and it's a constant times the function y1 plus some other constant times the function y2. Suppose I have a bunch of linear, they're essentially linear homogeneous equations that behave like that. So if I take the derivative of the first function, I can create it by a linear combination of two functions, and the derivative of the second function is some other linear combination of the second function. Now what we can do, you might notice, is we can put these guys in matrices. You'll notice that this is what's going to happen if we were to do that, assuming you know matrix multiplication. So now you might say, well, what would a solution like that, a solution to this look like? For reasons that I explained last time, an exponential seems to make sense. So here, if we guess a solution of the form, let's say it's some other vector, ef times the exponential to the lambda t, let's say. Let's pretend that something like that is actually going to solve this solution. Now I have to vectorify the assumption. So I turn the coefficient into a vector so that I can split it across the y1 level and the y2 level. What would that actually mean? Well,
Sorry, is that e variable different from the exponential?
no, that's the e that you need.
Okay.
So probably this e here is a constant. Let's use something else. M n. I don't know. See, this is why people use Greek letters, and then I use them and I get in trouble. So now that would mean, of course, if I assume my y, now my y vector is what the y1, y2 is doing. If I assume that it looks like that, notice that y prime is going to look like, well, you differentiate each part. So that gives me this side over here. Now, that is going to be, if I differentiate this, I'm going to get m lambda n lambda times e to the lambda t. And if we plug in to, let's call this equation 1, what do we have? Well, we'll have m lambda n lambda e to the lambda t equals a, b, c, d times m n e to the lambda t. I'm just plugging this into there. Now what you'll notice is, this is just a matrix equation, e to the t, e to the lambda t is never 0, so I can divide both sides by it, so you can ignore that. What you would get then is, here's a scalar, I can factor that out because vectors work that way, equals a, b, c, d times this vector here. Now, if I call this vector, let's call it just x, what I have is a constant times the vector x is going to be some matrix times the vector x. This becomes an important equation for us to be able to solve. Now, how many of you recognize that equation? At the end of 392, they're gonna bring this equation up out of nowhere. This is the equation used to solve for eigenvalues and eigenvectors of a matrix. Why is that important? Because of this. That's why it's important. So at 392, they're just going to say, they're going to start you here, and then they're going to say, here's how we solve for the lambdas and the x's, and hey, by the way, you can plug these into an exponential and get a solution to a system of division. And they're not going to tell you why. This is why. If I pretend this is a solution, the calculations say I need to be able to solve this equation. That is finding the eigenvalues and eigenvectors. And the 392 lecture that I asked you guys to watch actually has me starting here and explaining everything from here. So I'm not going to do that. But that's how we got here in the first place. And why it actually attaches to that. And why when I find a lambda, I'm going to plug the eigenvector in the coefficient and the eigenvalue in the power. And why it would look like a linear combination of them, because now I'm going to find two lambdas, and I know a linear combination of the solution is a solution. And that's why 392. If any of you are doing it, it's going to be one of the last things you do. When your professor starts telling you this, you're going to, that's what was going on. Because they're not going to tell you. 392, they're not going to tell you. Like, even I don't tell my 392 students what went on. But this is what went on. We assumed the solution, we got to this point, we solved this, that's called finding the eigenvalues and eigenvectors. It goes back and plugs into that, and then we take a linear combination to solve the system. It's coming together. Hold on. Now, again, more hand waving. I'm going to just tell you, in general, solving first-order linear systems are, I don't want to say easy. They're easy. The proof of why we can always solve them isn't easy. It doesn't only work for constants, it will actually work if your A, B, C, D are functions, as long as they're continuous on the region where you want to find it. We have methods for actually solving the system. So, this is what we can do in the case where everybody's a constant. With continuous entries is understood. So, again, like I said, it's a very hand-wavy lecture. Like I don't expect you to fully grasp what I'm saying, just have an idea of what I'm saying, and I am happy. So now, that's good. We know how to solve a first-order system of linear equations. It could be larger, but this kind of idea would work in the constant case. In the function case, we need something more sophisticated. Sometimes we have to use series solutions and all kinds of stuff. But we know how to do it. It's a problem that we know how to solve. In 392, they ask you to solve a specific variation of this kind of problem. But in general, we can do it. Now, let's start to bring it back. Suppose we have a linear Nth-order ODE. Of course, whatever I say here is going to apply to the second-order case. Say I write it in standard form, and I can bring all the coefficients to the other side. So it's going to look like y to the n is something like a n minus 1, y to the n minus 1, plus a n minus 2, y to the n minus 2, plus dot dot dot, all the way down to a 0, y to 0, homogeneous. So there's no extra function without y's. We'll deal with that when we'll deal with that situation. But for now, I don't want you to worry about it. Here's a cool thing you can do. You can create a system of equations from that one equation. Well, here's what we're going to do. I am going to call, say, y1 is my y to the 0, my y1, my y prime, y2 is the first derivative, y3 is the second derivative, and so on and so forth. I would get up to the fact that my yn we actually call this y0, y1? So it just goes with the derivative y2, yn minus 1, I can think of it as just the n minus first derivative, right? Now, what you would end up have this be is that my y to the n can now be written as a constant times the yn minus 1 plus all the way down to a constant times the y, 0. And now what I can do is do this. Create a vector that's going to hold all of these derivatives. So let me put the y to the n minus 1 here, the y to the n minus 2, all the way down to the y to the 0. And notice that here, if I take the derivative of this, I'm going to bump up all these guys by one derivative. So what's going to happen is that's going to give me the y to the n minus 1, all the way down to the y prime. Now, what does that actually do for us? In particular, this is going to be, well, the y to the n is that whole thing. And then these guys I just take to be themselves. So down here I have the y to the n minus 1, I'll have the y to the n minus 2, all the way down to the y prime. You'll notice what I can do from there is via matrix multiplication, I would have the coefficients here, n minus 1, all the way down to a 0. I would have 0, 1, 0, 0, 0, 1, 0. And this pattern of 1s will continue all the way down to here. And over here, I'm going to have the yn minus 1 all the way down to the y1. Now, what you'll notice happens here is that this guy is the derivative of some vector. Call it the derivative of y. Which vector is it the derivative of? Well, it's the derivative of this vector. So that's y. I literally just created a first order linear system from an nth order differential equation. This gives y prime equals some big matrix, which is this particular matrix, times y, which is this matrix. That's a first order linear system. We can solve this. In fact, when the determinant of that is non-zero, we can solve it uniquely. So this means, now again, a lot of hand waving happens here. We're really out of time. Hand waving. The unique solution to this can be found. Why? Because we can solve all of these guys. They're not a problem. Now, what would that solution actually look like? Now, your y is going to be, well, it's going to be a vector with n functions in it, right? Let's just not remove notation and conflicts. But yeah, ultimately I'll be able to find a vector with a bunch of functions in it. There will actually be n functions. Now, if I have some initial conditions and I start plugging in constants into numbers into these functions, they'll all turn into numbers. Everything will reduce to numbers, and I end up in a Cramer's rule situation where it's just like, find the determinant and do that. So once you give me a list of with initial conditions, collapses into a Cramer rule situation, lots of hand waving. And technically these functions here, they are derivatives, but they're going to be single variable functions. You can just integrate them as many times as you need to get to the original y1, y2, blah, blah, blah. But ultimately, what you're going to have happen is there's going to be a list of n functions that make the original nth order differential equation work. Could there be less than n? No. Could there be more than n? No. It's exactly n. It's a matrix. That's what it is because of matrix multiplication, because of how matrices work. It has to be n of them. And so this with more hand waving gives us, and this is the last thing I'll write down and then I'll let you guys go. And we'll continue this discussion next time.
That coefficient matrix A looks like the identity matrix, but.
Well, only a part of it. Like the first row is there's a bunch of other things. It's gonna have an identity in the middle part.
Offset of.
Yeah. This with a lot of hand waving gives the existence of uniqueness theorem for nth order linear ODEs. It says the following: given any nth order linear ODE, it is guaranteed to have a unique solution fulfilling n initial conditions.
So this is just harkening back to the, when we had a second order ODE, we needed to.
Yeah, just think of what I did, but it's a 2 by 2 matrix all the way. So
Okay.
I just have a vector
We're
2.
only getting, right now we're only at the second order ODE, so we just
Yeah.
need a 2 by 2 matrix.
Yeah.
Right.
But I just want to prove it kind of in the nth case and then just say the 2 is a special case,
I got
right? The 1 is an even more special case. You can't really do this treatment with first order ODEs. But once we have an nth order where n is higher than n is greater than or equal to 2, this theorem will take effect. I mean, it does take effect more in general. But the argument for why it takes effect for n equals 1, it's a different argument. You can't really use the Cramer's rule. But I'll talk about what you would do in the first order case more specifically. But we're in the middle of second order, so this one is more relevant. Where all the AI are continuous on an interval I, you need the continuity, or this whole thing breaks down if you don't have continuity. So if all the coefficients are continuous, of course in the constant coefficient case, constants are automatically continuous. So you're given that with continuous coefficients with initial conditions. Y of t0 equals y0, y prime of t0 equals y prime 0, up to y to the n minus 1 of t0 equals y to the n minus 1, 0. So given that with continuous coefficients and initial condition, there exists, that's the existence part, a unique solution How would I find that solution? Well, this vector, plug in these numbers into that vector. That's going to be that one coordinate that's going to solve it. That solves the ODE on I. And it will consist of n linearly independent functions, and it will be n times differentiable.
So this kind of matrix, would it look a little bit like,
Well, if they're not, what?
no, you can finish, I'm sorry.
That solves the ODE on any interval where it is continuous. There will be a unique solution guaranteed, given by this vector that I just erased. It is y of t equals c1 y1 plus c2 y2 plus cn yn. It is n times at least differentiable and the yi's are linearly independent, meaning they will not be redundant. You need all of them. You can't create one by a linear combination of the others. And this is kind of why you know you have an nth order linear differential equation, there will be n linearly independent solutions, where the general solution will be given by an expression like this. And the general solution means every solution that you can come up with is expressible as that way, because there's only one vector that's going to give us that solution. By the Cramer rule. Yeah.
All of the initial conditions have to be with respect to the same t?
Yes.
Okay.
If we were to actually set one of these up, let's say with like the question that we had in the quiz, where we had some initial condition y of something is equal to something else, and then y prime of something is equal to something else, would one of our rows be the first function, and the next row be the derivative of said function?
Yes.
And then we can just do matrix algebra
Yeah.
with those things.
Yes. And you can integrate within the components to get to the original.
Say that again?
Because when you find a solution, it's going to look like a y1 and a y2 prime and a y3 double prime. And, so I can find y2 by just taking the first integral of that. Find
Right.
y2 by taking the second.
Okay.
Because it gives you in derivatives. Remember, when we translate back to the original, we had it in terms of
So we're going to use Cramer's rule.
But
Find
this
only
guy,
one of those.
but we'll know exactly that that guy matches up some function. I'll be able to integrate that function.
Okay, that'll be an easy to integrate function.
Yeah. No, it's not always easy. In fact, you can't always guarantee that the solution is elementary. So,
I'm trying to see it.
anyway, what I wanted to get across here is you have an nth order thing, there's going to be n linearly independent solutions. So I know if I have a third order and I only find 2 solutions, there's one more I'm missing. Right? Once I find 3, it doesn't matter how I got to them, I don't need to look for anymore. That's everyone. Right? Assume that they're all linearly independent, which I'll tell you how to check that.
We could use that other technique that we now know as well, right?
Come again?
The one that we learned last week.
Reduction of order
Yeah.
can work in some situations, yeah. It's not a universal technique.